So, welcome to the next video. So, in this video, I'll be solving another KTU previous year problem. This is from S3 MoS Civil. This was asked in 2018 December for 5 marks. What are beams of uniform strength? So, this is also applicable for 2019 curriculum students also who are currently studying in KTU. So, basically, what do you mean by uniform strength, which is for 5 marks? So, a statement will not be enough for your to getting 5 marks. If it is 2 marks question, a statement would have been enough. So what is beam of uniform strength? So it's a beam. It's a beam in which all cross section along the length will have same bending stress. Okay, so that means we know that when a beam is subjected to some bending moment. So let's say, I'll just explain this what it is. So if you have a cantilever beam, there is some load which is causing it to bend. Okay, so the bending moment diagram, because of this load, will look something like this. So if you're familiar with bending moment diagrams, this is module 3. You should be able to understand this. Otherwise, you can study that. So this is a bending moment diagram. The maximum bending moment will be P into L, where L is the length of the beam. L is the length of the beam. Okay, so this is a bending moment diagram. Bending moment diagram. Now we know that this beam is having some cross section. Let's say it's a rectangular beam of some cross section. Okay, so that means at different cross sections we have different bending moments. So if we take this cross section, we have this bending moment. This is the value of bending moment. If we take this cross section, we have different bending moments. So this is M1, this is M2. Okay, this is linearly changing. The load is like that, so it is linearly increasing. Now the stress at any location of the beam. So let's say if you want to find stress at any location. Okay, so I'll draw the beam again. So this is a neutral axis. So if you want to find, let's say, stress at this location, okay, stress at this point, what you do, you find the distance of this point from the neutral axis. I'll call that as y. Okay, then you use the bending equation, m by I equal to sigma by y equal to E by R. So in this portion only we have to use. So whatever m is there, so if you want to find at 1, so I'll call this as 1, at 2. So in the section 1, so section 1 and section 2, the cross section looks like this. For section 1, I'll call the stress as sigma 1. You can find sigma 1 equal to m1 upon I into y. So this y is this distance. Okay, and stress at section 2, I'll call the sigma 2 equal to m2 upon I upon y. Okay, so this is how do you find stresses at different points. So basically, since m1 and m2 are different, the stresses at this point, so we can see the cross section of the beam is same. The y distance from the centroid of this point is same for here and here. So I and y are same. So only thing that that is changing sigma is m1. Since m1 is changing to m2, sigma 1 is changing to m2, sigma 2. So if the beam is of uniform strength, what happens is these two will be same. Okay, sigma 1 and sigma 2 at a given point will be same. Now what is so then if this is same, so that means something else also should be. So let's say we'll assume if you want this and this to be same, and but these two things depends only upon m1, it is not possible. That means we have to change I, which have to change I as the beam change, the length, the location changes. So at different locations we have to provide different I. How do you get different I's? We have to change the cross section. Okay, so generally when we find beams of uniform strength, we will find the extreme stresses. We will find the extreme stresses. Okay, so the beam in which all cross section along the length will have same bending stress, or we should say same maximum value of bending stress. Bending stress. Okay, all the cross section will have same maximum value of bending stress. So where will be bending stress maximum? At the top and bottom. So if I draw the bending stress diagram, it will look like this. for any moment, the bending stress diagram will look like this. The variation of bending stress. So bottom, in this case, top will be tension. It's a cantilever, so top will be tension. And bottom will be compression. Okay. So since for bending equation, we can find stress at any point, but for beams of uniform strength, what we will look is only on the extreme stresses. Okay. Okay. So extreme stresses, the value of stress will be same at all the cross sections. That means I have to change the cross section at different locations. Okay. Then only I'll get maximum stress at the extreme fibers. Now, how do I change that? Okay. So this problem, you have to write this statement. Along with the statement, you also have to write, you have to show an example. Okay. So we will take the same example. Here in this case, what will be the maximum stress? So let's say we will keep the depth of the beam constant. Keeping D constant, we will vary B to get different values of I and Y. Okay, so basically we are going to vary these two also, but only thing that we are seeing is we will keep the depth of the beam constant, we will change the width of the beam. Okay, so let's say in this case, the first case, the maximum stress is given us. So in this diagram, the maximum stress is sigma, which is nothing but m by I into y. So nothing but y is nothing but d by 2. Total depth is d, y is d by 2. So m is the moment here. The maximum moment will be p into L. I will be bdq by 12. Y will be d by 2. Okay. So this gives me maximum stresses P into L upon BD square into 6. So 6 PL upon BD square will be sigma maximum. So maximum stress for this at this location will be 6 PL upon BD square. So what we will see, we will try to make a beam such that at all the cross section we will get this maximum stress, that is 6 PL upon BD square is the maximum stress. Okay. So what we will do, we will take a random cross section. So we will take a random cross section at x distance from this end. Okay. What will be the moment at this location? The moment at this location will be P into x. You can see this P into the distance will be the moment at this location. Okay. It is negative. So we will consider sign here. Okay. So P into L is the moment at that location. So maximum stress at section x distance from tip equal to sigma is equal to whatever m at x upon I of the section at x into y of the section at x. Okay. Since, so we'll call this sigma x or sigma max, sigma x. Okay. Maximum stress at section x. So what is mx? Mx, this is nothing but P into x. What is Ix? So Ix is, so basically what we are trying to do is, the depth of the beam is same, the width we will change. So width I will call as Bx. Bdq by 12 is the cross section. So Bx into dq by 12, and y also will be d by 2. So this also will be same because the depth is constant. We are assuming the depth to be constant. Okay, so this gives me equal to 6 px upon bx into d square. This is the maximum stress. Now, for a beam of uniform strength, the stress, maximum stress at all the cross sections should be same. So that means I can equate this and this. Okay, so when I equate these two, what I will get? 6 px upon bx into d square equal to 6 pl upon bd. So this one bd square. Okay, so now I can cancel out a lot of terms. So 6 p d square d square. So that means the width of section at any location. So what I will get, what is remaining is 1 upon Bx equal to L upon B, or I can write Bx is equal to, sorry, there is an x also. Okay, Bx is equal to B into x upon L. Okay, this is how width of the section changes. So at x is equal to 0, the width of the section is 0. At x is equal to L, the width of the section is nothing but original B. Okay, original width of the section. So how does it look? It will look like this. If I draw the plan, it will look something like this. This is the plan. This is the load point, and this is support, and this distance is D. Okay, if I draw the cross section, it will look like this. So this is L, this is also L, this is D, and this is the point load P. Okay, so beam looks like this. At different cross sections, we have different width. So in the end, we have x is equal to 0, this is x is equal to 0, and this is x is equal to L. At x is equal to 0, we have no width. At x is equal to B, x is equal to L, we get the width as B. Okay, but if you look from this side, what you will see is a beam, regular beam like this. But it is actually coming out. It is it's like a triangle from the plan, and it's a normal rectangle from the side view. Okay, so this is the beam of uniform strength. Now, on what all things this will depend upon? So this will depend upon the moment, bending moment diagram. So as bending moment changes, the moment changes, the stress also will change. So according to bending moment diagram, we have to vary the shape of the beam such that it will have same stress at all points. Okay, so if it was a UDL, the change would not have been like this. Okay, so for this 5 marks question, what you have to answer is, you have to answer this statement, then you have to do this small derivation if you have to do. If you don't want to do the derivation, if the end result also, if you draw as an example, this is a beam of uniform strength for a cantilever beam with point load, tip point load. If you write this also, it is fine. But this derivation won't take much time. It is safer to do the derivation and close it. Now, if it was UDL, it will be different. If it is a simply supported beam, the shape will be different. Okay, so different shapes are there. Let's see if there is a previous year KTU problem related to that. I will solve that also for different loads. But this is the idea. The idea is maximum stress at each location. Now, what happens if you if the bending moment diagram is still like this, will be the same shape. Okay, but what happens? The maximum stress at different location of the beam is same. The maximum stress value is 6 PL upon BD square. Okay, so I hope this is clear. We will solve another KTU problem in the next video. Thank you.